To understand the dynamics in the region of the parameter space where a fixed point is not reached, let's first look at the special case where the competition parameters add up to 2. Here the analysis is a little bit involved, but it's quite straightforward, and something magical occurs in this special case. And as we've seen in the case of two-species competition, there's some simple technique one can apply to quadratic equations of motion that often lead to some simplifications or some new insight. And the same thing happens here. So again, our equations of motion are written on the upper right. And let's first consider the equation of motion for the total density, n, which is defined as n1 plus n2 plus n3. And let's look at the equation of motion for capital N dot. If we add up the equations on the upper right, there's first of all the leading linear terms, n1 plus n2 plus n3, so that's n. And then we have minus, then you see there's quadratic terms. There's minus n1 squared plus n2 squared plus n3 squared. And then there's the terms that involve alpha, and if we add them all up, we'll find alpha n1, n2, plus n2, n3, plus n3, n1. And similarly, terms with beta, and it's exactly the same thing. And now to simplify things, notice that the first quadratic term almost looks like n1 plus n2 plus n3 squared if we include all the cross terms. So if we put in the cross terms, we'll get capital N minus capital N squared. And then we have to add back the cross terms that have been subtracted out by incorporating this into the perfect square. And with a little bit of algebra, you'll see right away that what's left over is 2 minus alpha plus beta times this quadratic form n1, n2 plus n2, n3 plus n3, n1. Now, in the special case where alpha plus beta is equal to 2, then the last term just simply vanishes. So this is just equal to n minus n squared, a much simpler equation. And we know the solution to this equation because it's just, again, the equation for logistic growth. And the solution is n of t is equal to n of 0 e to the t divided by 1 minus n of 0 e to the t minus 1. And so as t goes to infinity, the exponential dominates, and we see that we just get 1 as t goes to infinity. But now there's another trick that we can apply, and we've seen this before in the case of a two-dimensional system, is that instead of dealing with the equation for little n1 dot, little n2 dot, little n3 dot, let's divide on both sides of the equation, for example, for n1 dot, divide it by n1. So n1 dot over n1 is the same as logarithm of n1 dot, but it obeys a linear equation. So if we take log of n1 dot, we just get the linear terms on the right-hand side, 1 minus n1 minus alpha n2 minus beta n3. We can do that for the other two variables. Log n2 dot is equal to 1 minus n2 minus alpha n3 minus beta n1. Log n3 dot is equal to 1 minus n3 minus alpha n1 minus beta n2. And as before, let's add up these equations and see what we get. So on the left-hand side, we have log n1 dot plus log n2 dot plus log n3 dot, which is nothing more than log of n1, n2, n3 dot. Let's define the product n1, n2, n3 as p. So this is the same as log of p dot. But on the right-hand side, if we add up everything, there's 3 1s, so there's 3. And then we have minus n1, and there's a 1 in the first equation, a minus beta, a beta in the second equation, an alpha in the third equation, and so we'll get 1 plus alpha plus beta. And then the same thing, minus n2, 1 plus alpha plus beta, minus n3, 1 plus alpha plus beta. But if alpha plus beta is equal to 2, then 1 plus alpha plus beta is equal to 3. And so this is nothing more than 3, 1 minus n. But if we go back to the equation for capital N, we have n dot was n minus n squared. We divide through by n, and we also have the equation that log of capital N dot is equal to 1 minus n. And so in fact we have a conservation law because log n dot is simply related to log p dot, and the conservation law is 3 log n dot is equal to log of p dot. And so from this, we can immediately solve for p as a function of n. And the solution is that p of t is equal to p of 0, n of t cubed divided by n of 0 cubed. Now we've seen that in this limit alpha plus beta equals 2, that n of t goes to 1 as t goes to infinity. So p of t goes to the constant p of 0, n of 0 cubed. I'll define that constant to be capital C.